Well, thanks for having me here tonight. There are a lot of stories that you either see in the media or hear sometimes stories by word of mouth. And so I thought, and I'm happy to be here, actually talk about some of these stories. But first, I have to show you this disclaimer. You see a lot of my data, a lot of them are from me or from our group, but maybe not everybody, they do not necessarily reflect the opinion of everybody at NREL. So I'll cover durability and degradation rates. It's a slow, steady decline of performance over time, reliability and standard development, and some field failure and performance. The motivation for all this is the DOE sunshot goals of 2030, where durability plays a critical role. And what you see here is today, or like this is shown at 2017 there, 6 cents a kilowatt hour for utility scale system. The goal is to get it down to 3 cents a kilowatt hour. So how do we go there? That's shown, broken down in this chart here. There's module price in red on the far left there. That has, of course, a big influence. If we can decrease that price, we have a good chance to get there. Then there's a balance of system cost and soft costs. They are actually the biggest driver. And the next one, actually, are degradation rates and lifetime. And that's really my area of expertise. But there's also O&M failures. They go into this portion. And I work in both of these areas, and they're somewhat overlapping. But they also feed back into the soft costs because they're associated with risk. So if you have a higher uncertainty associated with your degradation rates, that feeds directly into the risk and higher interest rates that you may have to pay for an investment. And then on the right is shown a graph. The assumption that feed into this graph on the left are actually shown on this orange point there. And you can play around there, this module price versus the total area efficiency and different degradation rate curves. So if you want to change the assumptions a little bit, for example, if you drop down a little bit in module price to 10 cents from 25 cents a watt to 10 cents, then you can still achieve the 3 cent goal, but can get away with a 30-year lifetime and 0.5% degradation. So you can play around with the variables there a little bit. Now that's the motivation. And so in the first part, I'll cover degradation rates. And the first slide I want to show you really is degradation rates is typically as a percentage per year decline. And that's relative to the previous year. We also hear often module efficiency, that's measured in percentage. And sometimes there's a confusion about those because typically we drop the absolute percentage and the relative percentage just to make it challenging. Because I've seen actually my work misquoted where it was said that if you have a 20% efficient module and lose 1% every year, after 25 years you have nothing left. Wrong, because it's the 1% relative to the previous year. So the record efficiency for module is right now is 24.4%. If it declines at 0.5% per year, that's the green line. After 25 years, you're still at 21% absolute efficient. That's not bad. If you even go to 1% degradation, you end up still with about 18% efficient module. That's still very good. Aging is a reality of life. I think we all know this, right? If I had given this talk 10 years earlier, I would have had a lot more hair on my head. So on the left is shown, this is something I published in 2011. So I collected all degradation rates that I could find, all the published data, and put it in one histogram. And I found that the median degradation rate that we found was 0.5% and the average 0.8. So this distribution is a little skewed. And on the right, in 2016, I published an update on this. We had a lot more data now. But a lot of them were not high quality data where people used the nameplate rating and only measured it at the end of the lifetime. If you use the nameplate ratings, you don't have really a measurement at the beginning, so that can be uncertain. But if you use data where you have a measurement before and after, the distribution is fairly the same. Interestingly enough, natural gas turbines degrade about in the same percentage range there. But for photovoltaics, the degradation rate depends on a lot of factors such as technology, of course, module quality, mounting, installation quality, and climate, and some of this I will talk about it in the next slides. The lifetime of PV, I often get approached. There aren't any studies of modules of 20 or more years in the field. There's actually a lot of studies of 20 and more years, and that's actually color-coded here by location all over the world, even up to 35 years there. And every year we see more of these studies. And actually only last week, a study came out of 35 years in the field in Switzerland. So every year we're adding more to this knowledge there. But inherently it's challenging to determine these degradation rates, because if you collect data, like shown here for this particular system, it's sort of a mess of data. And somehow you have to extract like a trend out of this. If you do a brute force approach and put a straight line, a linear regression line through that, invariably you end up with the wrong answer. And that's shown with these arrows that I'm pointing out. The real degradation rate is actually far different. So we have developed in the last couple of years a software tool that allows you actually to extract these long-term trends. And that's free and publicly available. And that's really two ideas. When you measure the irradiance, which is the radiant flux from the sun per square area, sensors that measure that can drift in the field, and that can lead to you wrongly assess how actually your system performs. And so they can drift over time. And so in our methodology, we from the location and the orientation of your system, we can model what on a clear day what the irradiance should look like. And then instead of using the measured irradiance, we actually use the modeled irradiance to normalize your PV performance. And what you can see here in this graph is the blue lines are the measured irradiance and the orange lines are the model irradiance. So on a clear day, it actually looks pretty good. And then on the next step, we only look at when the sky is clear. And then to calculate the degradation rate, you may have this seasonal cycles of your performance. So instead of, as in the previous slide, you put a line through all the data points, you put one line from, let's say, today to the same day the previous year and calculate that slope. And then you do this for the next day and for all the days of your data set. And we found this actually works fairly well. And you end up with a histogram of the center, which is then very representative to what your true long-term trend is. We found this methodology is very robust to this seasonality that you see, outliers, seasonal soiling, shading, and sensor drift. We made that software available. So if you have your phone and Google RdTools, you can find it. Everyone can download it and can use it. It's also easy to share it with colleagues from around the world. Yeah, it's if somebody has suggestions how to improve it, they can put their request in, and then the developers can peer review that. It had a tremendous impact on the consistency. So what's shown here in this graph, in the first round, we gave the same data set to a bunch of different analysts, and they all had experience analyzing this. And the results were not maybe quite as bad as throwing a dart at a dartboard, but there was a significant variation. And then we had a standard proposal that we had written up, a written documentation, and that eliminated some of the extreme outliers, but there was still a lot of variation. And the green dotted lines are what I call the holy grail of degradation rates, 0.1% per year. That's if to hit this interval is really tight. And so we used our software that we had developed and gave it to a number of people from all around the world. And we're pretty much hitting it, this interval. There's a couple data points that fell slightly outside. That's because some people used a shorter time range, or not the whole data set. I should have specified it in the first place. But the interesting part is also these were not all PV experts. So some of these people had never had analyzed PV performance data before, but they were familiar with the software package. And then there were some people that never looked at PV data before and didn't even know the software. And still we're hitting this interval. So that's really good. And with this tool, we can now look at some of these questions like what is the impact of climate? This is from a paper that I published in 2016. It's broken out by climate and color-coded by climate. And again, one means like one measurement. These data points use the nameplate rating, which can be uncertain. And 2 plus, this is either had continuous data or at least had a measurement before and after. There might be a little bit of trend there.
What's the 1 and the 2 plus again?
1 is one data point, so they did one measurement and had to use the nameplate rating. But the nameplate rating can have a module, let's say a 250 watt module, that's the nameplate rating. But that can have variation. So it could be 260 or 255 or 255, something like that. And so you're taking these data points are uncertain. You take this uncertainty into the rate too. So these 2 plus, they are more reliable because you made the measurement before and after. So now you actually have an actual measurement before. So there might be a trend there. It's a little unclear because there's a lot of noise in the data. For this particular crystalline silicon type, we did looked at different installations from different places, different mounting, from Australia to NREL. And we actually did find a trend depending on temperature. And we could actually, not only that, it was accurate enough that it allowed us to actually study the root cause of the degradation. Historically, when you look at reliability, it has more to do with the packaging of a module and less to do with the actual cells, the silicon cells. And so what we found in this study is that the cells were changing because hydrogen in the cells was moving around. So that was very interesting. Another interesting aspect of this, pointed out by these 2 arrows, because these 2 points are almost, this show almost the same degradation rate, yet one is ground-mounted in Colorado, whereas the other one is roof-mounted in Singapore in a hot and humid climate. And that points to that the mounting plays a more important role than we think maybe. And this is an interesting system. This is the Agassi School in Las Vegas, a desert climate, named after the former tennis player who founded the school. The interesting part is that they have the same modules installed on different types of buildings, different roof types, and different standoff distances. So the gymnasium and the building A, they have a large section of this array are actually close mounted on a metal roof, which tends to run hotter in the summer, or run hotter in general. And the other buildings are either on a thermoplastic coated roof, which tends to be a cooler roof, and a carport. We have 8 years of data on this, and that's the analysis shown on the left, but on the right is a summary shown. The degradation rate is actually in line with historical values of 0.7, 0.6% per year, which is actually very good for a desert location. But the systems that run cooler, the carport, that's building B, and building B and C, they actually show actually almost no degradation at all. So the mounting configuration, it's not just the climate, it's also how you mount the modules is important. And the further the modules are mounted away from the roof, the cooler they run. But of course, we have a roof-mounted system on our house, there's a balance you have to strike, right? And you can only move it that far away and it's starting to look awkward. But typically, the more you can move the modules away from the roof, the cooler they run. And that can have an impact on the long-term durability. So in the second part, I'll talk more about reliability, which is more like sudden failures or different failure modes. Oops, I just jumped a couple of slides. That's actually not a new subject. The Jet Propulsion Laboratory started this way back in 1975. And that lasted till 1986, and they went through these block buy programs. So their job was to reduce the cost of solar and increase reliability. So they went out and bought all the designs that were available on the market. They tested them, they field deployed them, looked how they failed. And then they fed that information back to the manufacturer and developed a new test for this. So they went around this cycle 5 times, and they increased the lifetime of modules from under a year to over 10 years in that time frame. And something that's really important that came out of this is the Design Qualification Standard, IEC 61215, that we still use today, and the Safety Standard 1730. Some of the tests that were developed during this time frame is shown here, divided by these different blocks. There's thermal cycling, humidity freeze, hotspot, mechanical load, and they're actually hail tested. So these modules have to pass this test. They have in the block 5, they had to withstand 10 impacts of 1-inch hail at 50 miles an hour. But it's quite a stringent test there. And some of these aspects of these tests to be still used today. But this design qualification standard is an evolving document, so I'm just going to click through this. This is from the 90s to today. This is from a colleague of mine. But you see, this is it's still evolving depending on what we see in the field. We still add to this standard, and it's still edited and it's still revised. So we're still going through this learning cycle where we deploy modules in the field, we observe what's happening in the field, and then feed it back into new tests. But one thing it doesn't do is, when the module passes the design qualification test, it tells you nothing about how long it's going to last in the field. That's a completely different test, or like a completely different science. It's just the design qualification test is only to eliminate early failures. But it doesn't tell you really anything about lifetime. Obviously, we can't wait 25 years to find out what happens, so we'd like to have a test so we can put a module in a chamber, maybe do a test, and then figure out how long it would actually last in the field. But you can't do it arbitrarily. Oops, looks like, here we go. You can't just arbitrarily extend the qualification test. It's really hard to accelerate 25 years in a single test. And depending on how you accelerate it, you might get, with this A, you get very different results. And so we call it these bake-out contests when I first started at NREL. So manufacturers would have, it's like the bread and butter test, like 1,000 hours in the design qualification test of damp heat, which is 85 degrees C and 85% relative humidity. It's a pretty difficult test. And the manufacturers extended them to 2 hours, 3,000 hours, 4,000 hours. And it was this bake-out contest, but we saw failures in 4,000 hours of damp heat that we've never seen in the field before. And so this is great if your module can pass that, but it's really meaningless because you never see this in the field. So this loop, what we see back and this feedback, what we see in the field is really important to develop these tests. And to develop these tests, we really have to understand the physics and the chemistry. So to specifically develop a lifetime test. There's a little bit about this 3-pronged approach. I talked about the durable design, that's the design qualification test. And they can be used in 2 ways. The manufacturers can go to a customer, can say, like, we passed all these tests, look, really good. Or from the government, can come from the government that can require that all the modules installed have to pass this test. like the California Energy Commission. But there's also, you need to have consistent manufacturing too. Durable design is the first good step, but you also need consistent manufacturing. You also need system installation, because a lot of things can go wrong in the system installation. And then once it's installed, operation and maintenance is very important too. You have to have, and NREL has this best practices for O&M that's available. That's a working group, and that's available, publicly available. For example, not every electrician is certified to work on PV. There's certified installers like NAPSEP is important. So there's a whole, there's a lot of things that go into PV reliability, but I get this asked quite a lot. Are PV modules from Asia more defective? There has been a lot of questions like this recently, and there was an article in the New York Times in 2013. A lot of people were interviewed. Actually, I was interviewed for this article too. And what we told the journalists, like, we don't have any evidence of massive failure of PV in the field, which unfortunately did not end up in the article. But I find it interesting, 2 days ago, this was published from PI Berlin. That's a company, obviously they are based in Berlin, Germany, but there's a company that goes out and audits manufacturing plants. So they go out to all the different manufacturers, and they have been doing this for over 10 years. And they just published this on Tuesday. And what you can see in the first graph on top is by how they rate the manufacturers by capacity. So the larger manufacturers do better than the smaller manufacturers, and they subscribe this to that the larger manufacturer has more, has better leverage on materials at a lower cost, and that could play into their advantage. But the bottom graph I find also very interesting, because they broke it down into geography. And actually what turns out is, like, the Asian companies in general tended to have a better grade than manufacturers from India, Europe, and US and Mexico. So I thought that was very interesting. And another interesting question that has been bothered me for a long time is the PV quality that's installed or used somewhere in the world is really the same. So when I look at studies somewhere else in the world, the results, are they really the same quality of the panels that we see in the US maybe, or in Europe, or in Asia? And so this is a little bit of a frightening story, and if you, I invite you to come up front here, because I have that panel up here. So this is a panel that we had bought for us in Africa. And actually it's pointed out by these arrows. The middle columns are actually printed out on paper. It's actually tricky, because if you put it out in the sun and measure the voltage is what the nameplate rating should be, but the current is half, because half of the cells are printed out on paper. And it's very tricky, it's very difficult to see. It's right here, so please come up front after the talk. The nameplate rating, or the nameplate sticker, has spelling errors. That's another giveaway. It also says IEC, but it doesn't specify which test IEC. And when you look closely, you can see actually the edge of the paper, and the interconnects between the cells actually don't really connect. They just end in no place. Yes?
So the CE label is phony as well, isn't it?
I'm not, probably yes.
That's the standard.
Yeah, the same with IEC, it's just doesn't specify exactly what it is.
The field of forensics frequently looks at things under UV light.
Mm-hmm.
And I would expect that to look very different under UV light.
Yeah.
As well as other types of counterfeiting.
Oh yeah. The problem is, like, when you buy this module, or when these people can buy this, this was bought on the open market, I should say. Nobody looks at it. As an individual user, probably doesn't look at it with UV fluorescence. But you're right, I mean, it probably would show up. Actually, if you look at it with a microscope, the actually working cells have a lot of cracks in it too.
Yeah.
The panel was probably not made in Toronto.
Great question. The short answer is we really don't know. We had clues it might come from China, but it's not clear because we found a distributor in South Africa who claimed that their panels came proudly from China. We have shown this panel to a delegacy from the Chinese Academy of Science. They were just as astounded as we were about this. So the short answer is we don't really know. We were in touch with the lawyers of the company, and they were also very surprised.
So it says counterfeit. Does that mean that it had a brand name that it was labeled with the name of a reputable manufacturer?
Yes, we believe so. And somebody, I mean, you can come up, when you look at the label, it looks like someone printed it out on a piece of paper and stuck it in there. But it's actually very cleverly made because, like I said, if you put it out in the sun and just measure it, yeah, it seems to work. It's just your current's half of what it should be. On to maybe better news. Before I got into what we more typically see in the field, this is maybe not as typical what we see, but what we more typically see, I want to spend just a little bit of time on PV module construction. On the left is silicon, on the right is thin films, and I have representatives of both of them here on the table here. Silicon, you typically have an aluminum frame, you have front glass, tempered front glass, and then you have encapsulant that encompasses the silicon cells. And then you have a backsheet and a junction box. For the thin films, they typically deposit the junction on the front glass, so the front glass is typically not tempered. But other than that, the construction's similar. You have a junction box. What you also see is on the thin film modules, you have an edge seal that prevents for moisture to ingress. What you more typically see in the field are this encapsulant discoloration, so they turn brownish. I have one module over here. It's been in the field for 30 years from Fort Collins. You see this browning in the center of the cells. On the edge, you can see it's not as brown. That's because oxygen diffuses through the back sheet and bleaches that discoloration. But that's something you had seen, especially in older installations, a lot. And on the right is actually a picture from a recent installation in China. And they also are very brown. And this is why we really need to have standards, because the problem of encapsulant discoloration has been solved 10 years ago or more. But because of price pressure and ever-changing supply chain, the problem can reappear. So we need to have standards so problems that are solved stay solved and don't reappear.
I'm not following you. Does the color mean something bad?
No, so that's a good question. You do have some power loss, and that's shown in the graph on the left. But typically, it has not a lot of impact on power. You do lose a little bit of power just because you don't get as much light through to the cell anymore. But other than that, the impact is not as big as some of these other failures. Delamination you can see, so sometimes it starts, you see this little white area along the bus bars of a silicon module. That's typically between the encapsulant and the silicon. You can also have it at the glass. That's shown in the next picture. Then it can grow over time, where it covers the entire cell. Moisture can ingress, can corrode the fingers and the bus bar, that's shown in the picture on the right from a module in Florida. And then you can have lamination on the backside, minor of the back sheet. So minor issues might be you see bubbles that form over time. You can also have chalking. You go deep with your fingers on, and you have white chalk on your hands essentially. But then if it gets more of a major problem, that's shown on the right, when larger sections actually these bubbles crack or larger sections come off, then it becomes a safety issue because now, when it rains, you can have the module can short out.
And the pressure from the bubbles is caused by what pressure?
Well, gas formation, so some chemical reactions happening in the module.
In the laminations, not in the actual solar cell.
Yes, in the lamination. This is what I was talking about earlier. Most of these failures modes have to do with the packaging of the module, not to do with the silicon itself.
And if we were to take a pin and pop the bubble, would that be no good?
That would probably not a good idea because now you have a hole and now you have pathway for moisture to get in. Hotspots, that's something you can see an infrared image. So they're shown on the left. There's several hotspots pointed out by the arrows. They can be caused by solder bond failure. So when the solder bonds between the cells starting to fail and the solder comes loose, they can come apart, and sometimes you see it on the back. You have a burn mark on the back. And they have, what's shown on the right, they have a higher impact than like the encapsulated discoloration. So when you have spots, you typically see a higher impact on power. They can also be caused by cracked cells. So on the left are some images from a module where you see some cracked cells. They're in by EL, so electroluminescence. You send current through the module and look at the module in the near infrared. You can see these cracks.
The thickness of cells has been going down. They actually
Yes.
lose thickness.
Yes, yes. And so what's shown here is what happens. This is done by my colleague, starring my feet there. You can see what happens if you walk on a module. So black is bad. So dark areas is where the module is not producing anymore. And you can see it when I walk on there and start hopping around on it, that it caused permanent damage to the module. And especially when you expose it now to the seasons, the thermal cycling, you'll see more and more these cracks can open up and have a more dramatic impact on power.
Maybe you're going to talk about this, but would that apply to hail, where the hail may not break the glass?
Great question.
Damage the cell?
Yes.
Okay.
So that can happen with hail. You probably all remember May 2017. We had 1¼ inch hail at NREL. Some modules were broken where the front glass was shattered. No, I actually have it. No, I don't think I have a picture of that later. But the front glass can shatter, and it's very obvious. But some of the impact is that you have some cracks that can form, but you only see it by EL measurements. They can grow later, but they don't have to. So this is a little bit of still research. There's some in the PV community that think cracks are really bad, and there's some people in the PV community that think cracks are fairly benign. The truth is probably that it depends on how the crack goes across the fingers and the bus bars, so it can have various impact. But yeah, hail can have an impact too. So in this slide, we want to look at what's actually what we see most, and you can see that reliability is changing. So 2010 and earlier, you saw almost the most important thing that you saw was encapsulated discoloration. Then in the last 10 years, the trend that we're seeing more and more is hotspots. Internal circuitry discoloration, glass breakage, and only then comes encapsulated discoloration. This is a little bit difficult because when we compare study to study, what I've seen a lot is there's no, sometimes people misidentify what the actual problem is. And so we developed this visual inspection tool. Again, everybody can download this with examples what a specific failure mode is. Because I've seen actually papers that were sent in for publication, and the authors argued this was a specific failure mode, and I sent it back and I'm like, no, this is the picture clearly shows you wrong. So the visual inspection tool helps with consistency between different researchers. In terms of complete failures, this is all taken what has been published. We see actually a fairly low rate of failures. Complete failures meaning modules in a state where we actually had to replace them. There was one study that showed a little higher failure rate. This was in a hot human and a roof-mounted area in Japan, but the rest, what we found is actually fairly low failure rates. And we could see the same result in a very large study. This is the section 1603. These are 50,000 systems totaling up to almost 2 gigawatt of capacity. That's shown here all across the US, colored by the year of installation. And so what we had is AC production data for all these systems. We had a predicted production. We had the location, at least rough zip code location. And we had comments to the performance. So the incentive was if the incentive program was such that they had to provide comments on the performance, and eventually we obtained the data. I have to do a little technical, but I have to show you this graph. You might have seen this on the left, a histogram. It's nice for one histogram, but if you have overlay multiple histograms, it's difficult to see. You can do the same representation on the right. It's called the cumulative distribution function. You actually stack up all these individual bars, and that makes it easier to compare different distributions. And that's shown here for this large data set of 50,000 systems. What's shown here is the ratio of the measured production over the predicted production, color-coded by the year, so from year 1 to year 4. And the median is the P50, so they have a 50% chance that the systems are above it. That's that horizontal, black horizontal line. And typically, those systems produced more than the predicted by 4 or 5%. And the P90, that means 90% of the system produced more than that, and it's about at 0.9. So most of these systems actually produced within 90% or better. And we currently have an update of this. So we have now 100,000 systems in this data set, which totals up to about 10% of all the systems installed in the US. It's quite a large number. Yeah, it could be. So that's a very good question. So what we see here is that the utility scale, so far if we calculated degradation rate on the P50, that the utility scale rates show more degradation rate that's closer to what we see on the module level, but the residential systems degrade more like in the 1.2% range. And we also found the same result last year, and when we had a different set of 500 residential systems, that the residential system showed a little higher degradation rate, but this is system degradation. So that could be shading, that could be soiling. Residential systems are not as well monitored as utility scale systems. Utility scale systems, large utility scale systems, they're very closely monitored. And so you could see this probably in here too. Good question. But they also had to provide comments as to the performance, and so we looked at this in terms of hardware, and the leading cause for problems on the hardware side were inverters. Then were other repairs, fuses, and modules. Defective modules were actually very low. We saw only 0.1%, and that's consistent with the number we had in that other study. We were not the only ones to find that inverters are more prone to failure. So on the left is showing a study by Sun Edison from 2013, and First Solar study on the right from 2017. So there's a whole inverter standard development in the process. It's a very comprehensive standard. There is also DNVGL, that's an independent engineering firm. They're doing a so-called inverter scorecard. So they buy inverters, they test them, they field deploy them, and then feed that information back into the standard. There's also the PVCAT, that's the PV Quality Assurance Task Force. That's an international collaboration that's working on this particular aspect, but also other aspects like UV, impact of UV or thermal cycling and so on. So there's a whole effort on improving inverter reliability.
You rate inverters?
I'm sorry?
You rate inverters by brand? Like some brands better than the other?
So this is what this independent engineering firm is doing. Yeah. They do the same on the module level. They test all the modules, and then they make this, again, it's available to everybody. You can go on the internet and find that. We also looked at some of these comments from this large data set concerned extreme weather. Lightning was high on the list, but the large impact was not lightning so much hitting PV, more like a transformer was hit in a substation that led then to the PV system being down with everything else in that area. Hurricane Sandy had an impact there. And I'm sure you were last year, the hurricane impact in the US Virgin Islands and Puerto Rico. So we had a team from NREL go down there. And so on the left is shown a PV system at the airport that had only a couple modules damaged by flying debris. But on the right, you had an array that was completely destroyed. Of course, location has an impact. So maybe it was location, but they also found that mounting can be an issue. So a lot of those modules were clamped. They were not bolted, they were clamped. You can see how the clamps got deformed from the winds. So that's why I said earlier, installation is a very important piece. It's good if you have a durable design. It's good if you have a consistent manufacturing. But installation is still very important and can have an impact on reliability. And then soiling, to clean or not to clean? Well, it depends, right? It depends probably where you are. Soiling is a very...
Did you study tracking systems too?
Yes.
In terms of the
absolutely.
reliability?
Yeah. So trackers, there's a lot of utility scale systems on one-axis trackers. There are two-axis trackers. I don't have any data specific on the reliability of trackers here. There's other people that I've been working with, working on trackers. But yeah, we look at that too. And so in the performance of on the right, you see these downward trends, and then maybe it rains, maybe a company comes out and actually cleans the performance jumps back up. Go ahead.
When they look that dirty, how much are you losing?
It depends. My favorite answer, and this is the answer perhaps. So we're looking at soiling in different regions of the US, and it's color-coded here. So green is not as much soiling. Orange and red, you see more soiling. So you see more soiling loss in the Southwest. Not so much in Colorado. So in Colorado, we typically see in the order of 1-2% loss per year. So it's not as much. Globally, the US is actually not as bad, even in the Southwest. You go to the Middle East, you could lose a lot more. I mean, you could lose 10-40%. Depending.
So at 1 to 2%, it doesn't pay in Colorado to clean it.
It depends on the size. It depends on the size. I mean, for a residential customer, probably not. But for a large multi-megawatt system, probably does.
Yeah, my experience at the Federal Center, watching those, it was too expensive to pay to clean them to get for the benefit.
Yeah, absolutely. Yeah. I actually have a picture of the Federal Center later.
That's why we have those pine trees that put that yellow dust. I looked up on my, I got gold collector.
Yes, they're really bad.
It took about some good rain and so on to really clean them.
So soiling is actually, soiling is a really interesting phenomenon. It can be very local under local conditions. For example, if you have agriculture right next to your array, it stirs up the dust and it's worse. We also found that actually in cities, the particle in the cities stick much more than like in the countryside. It can be also a global phenomenon. We had last year a group from Brazil, and they chemically analyzed the soiling in the Amazon. And they found that the soiling actually came from the Sahara. So it can be very global too. Go ahead.
Your second bullet says that the soiling losses are 1 to 2% per year.
Yes,
Do they
in Colorado.
Pardon?
In Colorado.
Yeah, here. But do they become cumulative if you don't wash them? I mean, does it continue to go down as they get dirtier?
It's an average value. So we get a good rainstorm, and it'll clean it off again. So on average, we see 1 to 2% loss. Maybe 1 year we'll have more, maybe 1 year we have less, but on average, so 1–2%. Other questions? Go ahead.
Could you say something about the relative degradation rates in module efficiency of thin film versus polycrystalline or crystalline?
Ooh, that's a good one. I don't have any slides on that. What did I say to that? It used, like, you go scroll back 20 years, and thin films had a higher degradation rate than silicon. Today, there's not a lot of thin film companies left. From what I've seen, they are in line with other silicon technologies. So it has changed. But unfortunately, I don't have any slides on that. Further, with speaking of thin films, so here this applies only to thin films, and this is not applicable to crystalline silicon, because you can actually create damage with partial shading when you clean these modules. So this is actually all done by my colleague Tim Silverman. He's been going around and showing this for years at different conferences, but there's still people who are surprised by this. So anyway, down at the left, you see a plant that was obviously cleaned during the day. And he went actually to the same plant and found an example there of a defect that probably was created by the cleaning. No, it's just a shade. So what I'm showing in this video here, on top is the visible image, and on the bottom is the photoluminescent image, so it's near infrared. And so every dark spot is where the module doesn't produce anymore. And you can see how essentially instantly you create damage, and that damage is permanent. Yeah, but it's easy fix. It's an easy fix. All you have to do is turn off the system and you won't damage it. Unfortunately, a lot of O&M companies apparently are not aware of that. So this is another thing where you have to be careful how you do it. And actually, they're working with the manufacturers and the IEC on a new test standard. There's also some solutions, some engineering solutions that you can work on. So this is work in progress, but
how much degradation resulted? We're talking 1 or 2%, or what?
It's more. How about that? And I'll leave it at that. I have analyzed some of the data on some plants, and it looks like more, but I will leave it at that.
So there were
Actually, when you look at the manufacturer, it says do not clean when it's on.
Well, usually to turn it off, you almost have to shade it, right? I mean, you just can't flip the switch.
Yeah, you can flip the switch.
Really?
Yeah. You could do it. You should just turn it off and then clean it, but apparently,
hit the breaker.
Hit the breaker.
Are there coatings that you can put on there to make them more rust resistant?
Yes. So that's that whole soiling. I showed you 3 slides. There's entire workshops on this topic. And yes, they're working on coatings to do this. There's also solutions where essentially it makes it vibrate and repel dust off the panels. So yeah, there's a lot of activity in that area, yes.
Might we assume that it would be cumulative over repeated washings, or would it be that one time it's the vulnerable spots and you then are dropped down your 3 or 5 or 7, whatever percent?
I would have to defer this to my colleague. I don't know the answer to that one.
Because otherwise you're going to...
I don't think that there's a limit. There's a limit, but I don't know where that limit is.
You said this does not happen on the standard
Silicon? No.
Well, so at my house, I always use that same squeegee to pull the snow off.
Yeah.
As soon as it stops snowing, you stop.
Yeah.
That's okay?
That's okay. Yeah, we've only seen this in thin films.
You have a lot of panels are thin film and poly, right, to get the higher efficiency.
A lot of, say that again, a lot
Are there a
of,
lot of panels now to get the high efficiency, your thin film plus the poly or monocrystalline? So they
that's a
have
good
both?
question. So there's, I haven't talked about this. There are thin films in development, like perovskites. They have shown a lot of promise. At this point, they are at, they look at cells, so fairly small cells. Some of them, they started encapsulating them and exposing them outside. They're not at the module level. I think that's more technology that's further out. But in conjunction with silicon as a double junction, that's more, I think that's more realistic to see this more in the next 5 years, perhaps. Yeah, so that's true, that could come. I've seen this already. I think ASU published something on that a week ago, where they put a cell perovskite on silicon and achieved record efficiency. So yeah, it does. But it's still at the cell level. It's not at the module level. We've had several discussions with Tesla on the shingles for about a year and a half now, and we haven't seen it. We've had plans to install them at NREL and haven't tested. We haven't seen it, so I don't know. I can't comment on that.
I'm thinking about states like Arizona where they have sandstorm.
Yes.
And how does that affect the treatment? How that really affect the
Yeah, you will get more dust on the panels, and then if you have a larger array, you probably want to clean that. You see that in Arizona sometimes. No, I don't. You Google. You do see over time. You do see over time at the bottom of the array, at the bottom of the module, you can see some abrasion that comes from the soiling, so you get this permanent effect. But it's fairly small effect on power in general. But you do see a little bit of abrasion then at the bottom. More questions before I go on? Yes.
As long as everybody's asking theirs. So do you have any info on what I would call mean time to replace? In other words,
Ooh, yeah, that's a good
Excel
one.
has got a 100
Yes.
megawatt park, and all they have to do is replace the panels, and they got a 200 megawatt park.
Yeah.
So as technology increases, I mean, are there any models to judge how fast that's happening versus the economics engaged?
You don't have enough replacements and failures on that to actually come up with a good model at this point. So there's still work in progress. I've seen on a couple older plants, 25 and older, where it just pays to just replace all the modules.
Right. It's like the wind.
Yeah. There's probably a bottom limit there because
What do you mean bottom?
there's a bottom because you have labor costs to replace the modules.
Sure. Yeah, that's it.
There's a lower limit.
As an undergrad engineering economics
Yep.
decision.
Yep, exactly. Yes, I have, from a degradation point, this is something I'm working on right now. We have some data on microinverters, and we have, for example, some modules in Arizona, in Phoenix, that are roof mounted. And they actually, I was surprised by that. We have some systems that show no degradation over 3 years. We only have 3-4 years at this point. Others do show some degradation. I think it has to do with the type of roof. That's why I said earlier on, I think not only the standoff distance, I think the roof type matters, but that's still work in progress.
So the study around that.
I don't have any data on that, no.
When you say roof type matters, is that
May matter, sure.
if it's white in each case? I mean,
Yes.
I think color matters
Yes,
a lot.
colors
I'm wondering
matters.
If you had color A and color B
Yes.
on 2 different roofs,
Yeah.
and the roof type was
Yes.
the culprit,
I think it all matters. I think the building the whole building becomes part of what's happening. You have convection going on, conduction, radiation. I think, but filtering out these trends is really difficult over your daily data noise. In this particular case, we have data. One is mounted with about the same type of color, but one is adobe, one is asphalt shingle. Asphalt shingle tends to run hotter.
Air pollution is a problem with stuff that will destroy the same glass windows that you have in. And I didn't see you mention that. Has that been considered in the studies?
Yeah, so for the soiling, I mentioned maybe briefly that we see in some of the more smoggier areas, industrial sites, you see the soiling tends to not be as easily washed off as in countryside. So yeah, pollution matters.
Well, you can etch stainless steel even.
Yeah,
I
and
mean, it's pretty aggressive.
yeah.
Do you know if there's degradation from ozone pollution?
I'm not aware of it.
NASA voices that analysts in space long after it all started. But they must be wrong.
For PV, or we have actually used some of their temperature measurement data, but they don't have, as far as I'm aware, they don't have any data on PV performance. Yeah. That cleans up fairly easily, actually. I know people who work on the solar cells that are deployed on Mars explorers. And because of you have no moisture, it cleans up much more easily than here on Earth.
Going back to the inverters for a moment, obviously there's a whole program that improve the quality of inverters, but I should know this, but do they degrade slowly over time, or is it more just one day they fail? And is there, I guess, if they do degrade over time, is there an easy way of testing their efficiency?
Yeah, so inverter. So inverter is a whole different topic. And what exactly fails? Typically, what fails in an inverter are the power transistors and capacitors. And so there are new trends coming on replacing the power transistors with wideband semiconductors. And so that could, they're better in switching. They can sustain higher temperature. So that probably has an impact on inverter reliability. But we're just getting to that point where this comes onto the market.
Actually, without all we in the talk.
I think I have a couple more slides. I was about to say, maybe I should finish my few slides and then you can keep asking. So, emerging topics. Bifacial systems are coming. This is a hot topic right now. Bifacial means that they can collect sunlight not only from the top, they can also collect the light from the backside. And the ground reflects sunlight back, and depending on what ground, right now we would have it's called albedo, and right now we would have really high albedo because it snowed today. So depending on the ground, you can have a significant amount radiated back. So on top is shown on the right a system in Oregon. Half of the system is bifacial, half of them is monofacial. We estimated in 1 year of production that you gain about 9% over the monofacial. So it's significant. On smaller systems, you see higher gains like this carport in Arizona because you get more light from all sides and it's higher up. So there's a lot of variables. Not only the ground matters, like how high it's up off the ground, what's the tilt, what's the ground. There's a lot of variables, and that's all in the works right now. Typically, we don't really know much about the reliability because most of these systems have been in the field for a year or maybe two, or maybe they're going into the second year. They should be similar to glass silicon modules, which tend to run maybe a few degrees higher, but they also collect more sunlight. So maybe there's a little bit of a trade-off. Another emerging topic is floating PV. NREL came out with a study a couple of weeks ago that showed the potential if you put PV on water in the US. And on the left is shown the largest installation of floating PV in China, 40 megawatts. That's a huge installation. And actually, Colorado got their first installation last year in Walden, I think that's near Steamboat Springs. But we don't know that much about reliability. There is a... Go ahead.
Floating PV.
Yes.
Has there been studies on the effect on aquatic life?
No. Well, sorry. Not that I'm aware of. Not that I'm aware of.
Sorry.
We're actually talking mostly about reservoirs. That's the big proposal.
Yes, yes. Okay. And the NREL study was mostly proposing on reservoirs. That's right.
It would seem to me that would be a good place to try bifacial.
I'm glad you asked because the graph is right there. So this is a study from Singapore where they actually have the same type of modules and array on water, on ground, and on a roof, which is very interesting. And in the middle graph, you see the ambient temperature. I have a hard time reading this on my screen here, but I think red is onshore, and blue is offshore. So the panels on the water tend to run cooler because you have water evaporates and makes the panel cooler, they produce more. But on the other hand, the next graph over is the albedo, and blue, so I'm glad you asked, is so the light that gets reflected back is much lower on the water than on the ground. So it probably doesn't make sense to put bifacial modules on the water. But there was the oldest installation I found. We have every year we have a PV reliability workshop, and I was the chair last year. And I talked because I wanted to bring somebody in with experience on floating PV, and the oldest array I was aware of was in Japan from 2010. And I talked to them, and they mentioned they had a lot of soiling, which is a little surprising because from all the water spray, they had to do a lot of soiling. And you can see this in the Singapore study here because you have a lot of bird droppings on there. They'll be coming to our reliability shop next month, so that'll be interesting actually to talk to them. Another thing from a reliability standpoint that they saw, the ground connectors, they saw some broken ground connectors. Obviously, if you put it on water, it needs to be done well. And some other interesting, fascinating field stories involving critters. Critters are attracted to the warmth of the PV. And so there's an example of rabbits chewing through the data. The magpie was damaging our panels by building a pretty solid nest behind the modules. And then squirrels, yes. Then you often, in big plants, if the maintenance is not done well, you can sometimes see sometimes bushes even or weeds growing between the panels. They can shade the modules. So then there is a good idea, maybe somebody thought, maybe I won't do a two-legged maintenance crew, but a four-legged maintenance crew. But I was surprised, and actually delighted to see this. Sheep are good. Goats and cows are not good. Goats are a little perky, so they tend to jump up on these things. And cows are kind of big animals, right? If they lean on something, they can break things. And then lastly, did you know that dead ends are corrosive? Again, they're attracted to the warmth. In the combiner box, when they die, they actually corrode the cables. So there's a lot of interesting observations that you can make in the field. All the things you never want to know about PV. So I do have a conclusion slide. So to see typically, this back to the serious part, and then I'm done. So we typically see degradation rates in the 0.5 to 0.8% year range, which is just not bad. We've developed an accurate and freely available tool to calculate those typical failures where we have to replace modules is typically low. In a large system study, we found most systems performed as expected. And I hope I've shown you that this whole field, the PV reliability field, is pretty active, but it stretches across the entire value chain, from the design to the manufacturing to the installation and O&M. And organizations like the IEC, IECRE, NAPSEP, and PVCAT help to continuously improve this whole effort. Thank you.
Thank you.